In this video, I want to talk about titrations and isoelectric pHs. Isoelectric pHs, also known as PIs. And the reason why, or specifically for amino acids, the reason why is because now we've talked about the structures of all the different amino acids, their abbreviations, and things like that. So now I want to kind of incorporate all the things that we talked about before involving the Henderson-Hasselbalch equation and sort of apply it to what we talked about with amino acids. So if you guys remember back to general chemistry, titrations were usually acid-base neutralization reactions, and they were used for a variety of things. In biochemistry, it's helpful to look at a titration of an amino acid to kind of sort of understand what role the pKa, the pH, and all that sort of stuff plays, and how that sort of determines what an amino acid will look like given a certain pH. So let me draw this titration curve out. So a titration curve will look something like this, where the y-axis will be labeled as pH, and the x-axis will be the amount of OH equivalents. If you guys remember back to just general chemistry, OH minus is a hydroxide ion, which is a strong base. So essentially, it's measured in moles of hydroxide ion, right, per mole of amino acid. That detail is not too important for understanding this, but it is that is the unit or sort of way to think about it. Essentially, what we're going to think about is having an amino acid at starting at a very low pH, for instance 0, and we're going to, which is very acidic, right? And we're going to continually add the strong base to it, and that's going to cause the pH to rise, right? So when we do that, we're going to track sort of how the pH changes and what the amino acid will look like at different pHs. So let me just split this up by 2s. 2, 4, 6, 8, something like that. So what I'm going to do is I'm going to draw specifically the titration curve. We're going to use the example of histidine. So histidine, if you recall, is one of the basic amino acids. So we're going to use histidine, right? And its 3-letter code is HIS. Its 1-letter code is H. So we're going to draw out histidine, starting from a very low pH all the way up to a very high pH. And we're going to track what it looks like at different points. So initially, if we have histidine at a very low pH, right? We haven't added any OH minus equivalents. We have a very low pH. That means we have a lot of hydrogen ions in the solution. So all the groups will likely be protonated. So if you recall histidine, let's draw this out. Histidine looks like this. If you were going to draw histidine at a very low pH, like a pH of 0, it'll look like this. It'll have its alpha carboxyl group protonated. Every group that's ionizable will be protonated. So over here we have the amino group. It'll also be protonated, and its side chain. Oops, I forgot to write the CH2 group first. CH2. And then we have the imidazole group, okay, with an N here, an N here, a double bond here, a double bond here, and if it's at a very low pH, it's going to be protonated. So we're going to track how this amino acid will look as we add hydroxide ion equivalents. So as we add base to a solution that contains this amino acid, what's going to happen? Well, these are all protonated, right? All these ionizable groups, this 1, 2, and 3 different ionizable groups, they all have particular pKa's. Now that means since they're all protonated and they have pKa's, that means they can act as acids. So if something, what would we expect to, which of these groups would we expect to be the first one to donate its proton? Well, things that are very good at donating their protons are strong acids, right? Strong acids have low pKa's. Which of these groups would we expect to be the strongest acidic group? Well, we know this is a basic amino acid, so it's probably not the imidazole group. I mean, it's probably not the amino group because amino groups are pretty basic themselves. The imidazole group is not as basic as some other groups, but it's basic relative to this carboxylic acid group. That is indeed an acid group. So we would expect that the first group to begin donating its protons would be this carboxylic acid group. So if we imagine this occurring, we would get this. So this is an acid, right? Here, this group here, and this is its conjugate base form. So this reaction has a pKa, okay, and we're going to call this pKa1. Okay, now the overall charge of this thing, that's another thing I wanted to point out. I wanted to track the charges of these different of the amino acid as the pH changes. So here initially, like I said, we're having it at a low pH. As we add OH equivalents, we're eventually going to make a bunch of these. Now here we have an overall charge of +2, and the reason why is because this is a positive charge, this is a positive charge, and this is a neutral charge. Upon this happening, upon the carboxylic acid group donating its proton, we have an overall charge of just +1, right? +1, +1, -1. So how many OH equivalents do we need to add to turn this into this? Well, that's the whole idea behind that question. Sort of requires that you answer what is an OH equivalent. Essentially, if we're adding one OH equivalent, that means we're going to take one acid group, and completely convert it into its conjugate base form. Okay, so what happens is the graph looks like this. As you add the OH equivalents, once you've added one OH equivalent, this is how the graph changes. The pH changes like this. So we have this kind of go up like this. And this is not perfect, mind you, but I'm going to do my best here. Okay, so actually let me draw the whole graph. Something like this, and then that's not great, but it's the best I can do for now. So what I want you to notice is I want you to know these things called equivalence points. So once we add one whole OH equivalent, right? I want to note that this way. Okay, so once we've added one entire OH equivalent, we have right here, right? This is the equivalence point here. Something like this. Okay, something like that. Once we've added one OH equivalent, basically what we've done is we started off at this point here, A. Let's call this point here A. Forgive me if this is not all making sense just yet, but it will, I promise. Point A, everything that we have, all the amino acid is at this very, very low pH, so all of it will exist in this form. But as we add OH equivalents, we're going to the pH will rise, right? And when that happens, eventually at a certain point, all of the amino acid of the histidine molecules that are in this form, right, will be converted into this form. Okay, so that's specifically what OH equivalent means. If you've added one equivalent of base for this acid, you've turned all of this acid into its conjugate base. So at point B here, we have nothing but this what's it called? This form of histidine. Okay, so if we add another equivalent of OH, what will we get? Well, if we add another equivalent of OH, we're going to get, oops, I forgot to draw this H here. Once we add that other equivalent, the next most acidic group is going to donate its proton. So between the amino group and the imidazole group, we should know that the amino group is going to have a higher pKa. So the one with a lower pKa, the imidazole group, will donate its proton first. So it'll look like this. The carboxyl group will remain the same. The amino group will remain the same. And then we will have the imidazole group deprotonated. So we'll just have that N. So now the overall charge of histidine is 0, right? Because it's just this positive charge and this negative charge here. So pKa number 2 happened. Okay, that pKa belongs to the side chain. This pKa1 belongs to this carboxylic acid group. Okay, so once we've added that second equivalent, right? That second equivalent, second equivalence point is somewhere around here. Okay, so once we've added that second equivalence point of base, we reach at this new pH here, something like this. Okay, so this point here, I'm going to call point C. Point C here, right? We have all of the amino acids will exist in this form. Okay, so here we have point C. Here is what we have this is at point B. This is at point A. Okay, so now well, now this amino group can also donate its proton, right? So let's just finish that off really quickly to kind of get an idea of what histidine will look like at a very, very high pH. So that's the only protonated group left. So it eventually, at a high enough pH, even the amino group will act as an acid and donate its proton. So then all of the groups will be deprotonated. Oops, I forgot that these N's have H's. Can't believe I messed that up. Sorry, guys. Okay, so there's an N there, and there. That N has an H. And now the overall charge of this histidine molecule is -1. Okay, so here's 0, here's -1. So now at a high enough pH, maybe, you know, somewhere up here, once we've added that third equivalent, right? Once we've added that third equivalent, essentially, we've added an equivalent for every single ionizable group. So there were 1, 2, 3 groups in their acid form. That means we must have added 3 equivalents of base to neutralize it completely. So where do these pKa's, how do these pKa's, these values come into play? Like, what role do they play here? So there must have been a third pKa. That third pKa belongs to the amino group. So if you remember back to the Henderson-Hasselbalch equation, the pKa was equal to the pH when the conjugate base concentration equaled the undissociated acid concentration. And essentially, when we look at the titration curve, the pKa will be the half equivalence point. Okay, so I want to note that here. The pKa will be equal to the half equivalence point. The half equivalence point. And I'll talk about what that means. So once we've added half an equivalent, the half equivalence point pH. So it's the pH at the half equivalence point. So once we've added half an equivalent, right, then what we have, if we add half an equivalent and we go over and we find that pH there will be the pKa. So what that means, though, at the half equivalent point, that means that, for instance, let's just think about pKa1. So as we add base, we're reducing the number of histidines looking in this form, and then creating more in this form. So as we approach adding a full equivalent, we're losing this and we're making more of this. Okay, because this acid group is donating its protons. So as it donates its protons, it's becoming to look like this. So, but notice though, at the half equivalence point, what should we have? Well, we should have half in the acid form and half in the base form, right? So that's exactly what pKa is. And just to sort of prove that to you, if you recall, right, the Henderson-Hasselbalch equation was pH equals pKa plus the log of the concentration of the conjugate base over the acid, right? So if we have the base concentration, right, equal to the acid concentration, right, that means we have half of this, half of the total histidines will look like this, and half of the total histidines will look like this, right? That means this value, right, these two concentrations are equal, right? And if that's the case, then we're taking the log of 1, which is just 0. So that basically tells us that the pKa is basically the pH at which these two concentrations are equal when we have half in this form and half in this form. So each pKa is just, the next half equivalence point. So this pKa1 corresponds to the point at which we have half of the histidines looking like this and half of the histidines looking like this. This next equivalence point here, right, I don't know where that is, something like that, 1.5, that next half equivalence point, that pH there is going to be our pKa2, right? So, and then over here, somewhere over here, we got it looking like that. Okay, this pH is going to be our pKa3. Okay, so what are all these values equal to? Well, this pKa1 is actually, the actual value is 1.82. So that means the pKa of this carboxylic acid group, right, is 1.82. The pKa of the imidazole group is 6.0 or so, or around 6, right? And that makes sense, right? This pH here at the second half equivalence point is 6. The third pKa is 9.17, and that's the pKa of the amino group, right? So notice that here, this pKa responds to the pKa of this imidazole group, and then this pKa responds to the last group that's acting as an acid to become in base form. Okay, so I didn't actually know where D was, so let me do that here. So once we reach this point here, that third equivalence point, that's where we have D, right? So at point A, we only have this, right? At point B, right, we've converted all of these into this, right? We added one whole equivalent to create it all into this. Then between B and C, right? Between B and C, we have this and this. But as we add a whole another equivalent, then we no longer have B, and then we just have C. Hopefully this is making sense. Once we're at this pH, if we add one more equivalent, we're going to convert all of these into these. So now I want to go through and add a few more letters. Let me do that in a different color though. So at point E, F, and G, what's going on? Well, at point E, we have half in the A form and half in the B form, right? We have half in this form and half in this form. At F, we have half in the B form and half in the C form. At G, we have half in the C form and half in the D form. Okay, so now hopefully that the pKa's and pHs and how they apply to amino acids makes sense. So you might be expected to draw the way a particular amino acid looks at a given pH. So now, how do we find this thing called pI? What is a pI? A pI, an isoelectric pH. So let's kind of separate this really quickly. So an isoelectric pH, or PI, is essentially the pH at which there's an overall charge of 0. Right? The true definition implies there's it's a little bit more complex than that. Oops. let me kind of make that a little bit more clear. There's an overall charge of 0. So we want if we want the isoelectric pH, or PI, of histidine, we want to know at what pH will this form exist, right? Well, if we want to find that, all we have to do is take the average of the pKa's that are on either side of that species, right? So this species is the one that has 0 net charge, right? If we just take the average of these two pKa's, then we'll get the isoelectric pH. So pKa2, so the PI for histidine will equal pKa2 plus pKa3 over 2. So our pKa2, if we look back over here, was equal to 6, and our our pKa3 was equal to 9.17. I'm just going to round things off to make it a little bit easier and divide that over 2. So 6 plus 9 is 15 over 2. Right, so at this point I'm going to actually approximate it, right? So the PI of histidine is approximately 7.5. That is the pH at which we would expect histidine to carry no net charge overall. Okay, so the reason why I did histidine here is because it's a little bit more complex than finding the PI for other amino acids, because other amino acids, they normally don't have 3 ionizable groups. This one has 3. If there are only 2 ionizable groups, you know, the carboxylic acid group and the the alpha carboxylic acid group and the alpha amino acid group, then you would just take the average of both of those. For instance, just a quick example, I suppose. A quick example for alanine. Alanine, the pKa of its alpha carboxyl group is equal to 2.34, and the pKa of its alpha amino group is equal to 9.69. So if we want to find the PI for alanine, the PI for alanine is simply these two pKa's added up together and divided by 2. So 2.34 plus 9.69 over 2, and we actually just get, what do we get? I forgot the value. Let me actually calculate that really quickly. Goodness. So we have, I can't do math, 9.69, whoops, 9.69 plus 2, oh my goodness, 9.69 plus 2.34 divided by 2, we get a 6.02 approximately. So the PI for alanine would just be 6.02. So that's much, much easier. Now what you could do for alanine is you can actually go through and kind of think about it this way, right? Draw its the 3 forms it can exist in, where the all groups are protonated, and then the first group to give up its proton is the carboxylic acid group. Then the next group to give it up would be the amino group, and then you would just take the pKa's on either side of the form that has the overall charge of 0, average them out, and get the PI. So I hope that was helpful, and I'll see you next video.